Hello and welcome back. In this video we'll be starting section 4.1 on exponential functions. So just as a quick review of exponents, things we've been working with all semester, let's evaluate a few exponents here. So if we have 2 to the first power, anything to the first power is just itself. Here we have 2 squared. Something squared is just it times itself, so 2 times 2 is 4. 2 to the third power is going to be 8. 2 to the fourth power will be 16. We're just adding factors of 2. We have 2 to the 0 power, and anything to the 0 power is just 1, except for 0. 0 to the 0 power is not defined, but anything else to the 0 power is always 1. We have some negative exponents, so we have 2 to the negative 1. When we see a negative exponent, we flip it over. So 2 to the negative 1 is going to be 1 over 2 to the first power, which is the same thing as 1/2. 2 to the negative 2 power is the same thing as 1 over 2 to the 2 power. Again, we just flip the fraction over, and this is going to be 1/4. And 2 to the negative third power will be 1 over 2 to the third power, which is 1 over 8. We can also introduce some fractions. So the 1/2 root of 2 is going to be the square root of 2. The 2 here refers to squares, so this is going to be square root. Here we have 5/3, so this is going to be the same thing as the 1/3 root of 2, or the cube root of 2. It's essentially the same thing, but we're raising everything also to the 5th power, so we can just add that on top of everything else. And then lastly, if we have negative exponents, everything works the same. We just have to flip over the fraction. So this is going to be 1 over 2 to the 1/7 power, and this is the 7th root of 2. So when we're looking at all this, what we can see is that we can take 2 and we can start raising it to lots and lots of powers. So we can make a function out of it. F of x is going to be 2 to the x power. For instance, f of 1 is just going to be 2 to the first power, which is 2. Or f of 0 is 2 to the 0 power, which is 1. So this type of function is called an exponential function. And an exponential function is any function that will look like this, where we have f of x is equal to b to the x power. B is called the base of the function, and there are a couple of restrictions on what b can be. B has to be positive, and it can't be equal to 1. And I'll go through a little bit of why we make these restrictions. So here are a couple of examples of exponential functions. So we have the function that we already saw, 2 to the x power, and here the base is 2. We have 10 to the x power, and again 10 would be the base here. So g of 3, for instance, would be 10 to the third power, which is 1,000. So we can continue on. We can see some functions that maybe look a little bit different. So here we have 3 to the x plus 1 power. So it's not just to the x power, but we still consider this an exponential function. The base is b. But we've essentially replaced the x with an x plus 1. This is just like a horizontal shift. So we've just shifted the function 1 to the left. And here, again, we have the same thing. Here we have a base of 1/2, whereas the rest of these had bases that were bigger than 1. This is a base that's smaller than 1. And we have 1/2 to the x minus 1 power. So again, it's the same as an exponential function, where we have an x up top. But here we have x minus 1. So it's as if the function has shifted to the right by 1 unit. It's just a horizontal shift. Let's look at some of these other functions which are not exponential functions. So here we have x squared. 2 is an exponent, but the variable must be in the exponent. Here, 2 is just a fixed exponent, so the exponent isn't changing. So this is not an exponential function. Here we have 1 to the x power. And 1 to the x power satisfies, okay, I've got a number down below, I'm raising it to the x power, but this isn't really an exponential function, because no matter what x is, 1 to any power is always 1. 1 times 1 is 1. Doesn't matter how many times you're doing it. So 1 squared is 1, 1 cubed is 1, 1 to the 1/2 power, the square root of 1 is 1, 1 to the -2 power is 1. So this is actually a constant function. So it is not an exponential function. Here we have -1 to the x power, and this again looks like an exponential function, but if we think about what happens if I start plugging in numbers for x, for instance 1/2, well, this is the square root of -1, which is the imaginary number I. Well, this causes some problems because we want to consider functions where if you plug in a real number, you get a real number. We don't want to see imaginary numbers popping out of here. So we also do not consider this an exponential function. This last function is pretty cool. This works well for positive numbers, negative numbers not so much. But this is also not an exponential, and not an exponential function, because the base of the function is not a fixed number. The base is x. So while this defines a perfectly valid function for positive numbers, this is also not what we would consider an exponential function. It's just something else. Next up, let's look at an example of how we might use this. The average amount, so this comes from the textbook, the average amount of money spent at the mall after spending X hours there is given by 42.2 times 1.56 to the x power. So on average, how much money is spent after 3 hours? Well, we just, it's given by this function. So if x is the number of hours there, I just need to plug in 3 for x. So f of 3 is going to be 42.2 times 1.56 raised to the 3rd power. And so I did this off screen, so this is going to be $160 and 21 cents. This is rounded to the nearest cent. When you want to input this into a calculator, there are several ways to do this depending on the calculator. What you would normally write, so in a calculator. I can't spell today. Calculator. You normally write 42.2 times 1.56, and sometimes there will be a caret button that will look like a little up arrow, and then you'll write 3. Or if I wanted to plug in 3.16 up here, for instance, I could write caret 3, and then that will give me the answer. Or some calculators will have another button, and the button will look like x to the y power. And how you use this is it'll be 1.56. You'll press that button and then 3, and then it should give you the same answer. So depending on the situation, there will either be a button that looks like a caret, as in like what you'd write in writing when you have to insert a word, or x to the y. So let's graph a few of these functions. So I'm graphing exponential functions. So let's graph 2 to the x power first. I can fit all this on the screen. So we already did all of these. We found all these values earlier. And so if I start at 0, we'll see that f of 0 is going to be 1, because 2 to the 0 power is 1. And then at 1, we'll hit 2. At 2, we'll hit 4. At 3, we'll hit 8. And you can see that as we go forward one increment, we're doubling every time. So we move forward 1, we double. We move forward 1, double. We move forward 1, we double. Going backwards, we'll see roughly the same thing. Whereas at -1, we're at 1/2. At -1/4, at -2, we're at 1/4. -3, we're at 1/8. So as we go back 1, we'll see that we get chopped in half every time. So from 1, we'll go to 1/2, to 1/4, to 1/8. And this trend continues in both directions. If you go to the right, you end up doubling. If you go backwards, you end up dropping by a half. And if we graph all of these points, if I can hit them all, we have an exponential graph. And this graph, this growth, where we end up doubling every time that we move over, this is what's called exponential growth. And as a mathematician, I have to admit that this phrase is overused by a lot of people that don't really understand what exponential growth is. But here you have it. This denotes exponential growth, and we can see that it doubles every time we move over. The reason that it doubles is because the base is 2. So we should think that we're doubling every time that we move over. If we look at the sort of opposite graph in some sense, we'll take 1/2 to the x power. So if I plug in 0, 1/2 to the 0 powers is always going to be 1. Anything to the 0 power is 1. 1/2 to the first power, anything to the first power is just itself. 1/2 squared, 1/2 times a half is a fourth. 1/2 cubed, a half times a half times a half is an eighth. And if we raise these to negative powers, we're flipping over these fractions. So 1/2 to the negative 1 power is going to be 1/2, but we've flipped it over. So it's going to be 2 over 1, which is the same thing as 2. To the negative 2 power, this is going to be 1 over, this will be the same thing as 1/2 to the second power, but flipped over. So this is 4 over 1, which is 4, or 8 over 1 if we're following this pattern. We get 8. So we can see that this function looks very similar, except for the fact that it's kind of going backwards. So I'll have to draw into that. So we have our exponential function. And what you'll notice is that every time I move forward 1, every time we go to the next number, we're being chopped in half. Why in half? Well, the base of this function is 1/2. If the base of the function was 1/3, and we had 1/3 to the x power, every time we move forward 1, we would be dropping down by a factor of 3. We'd be chopped into 1/3 of the original value. So this base here describes how fast we're either going to fall if this number is less than 1, or how fast we're going to grow if that number is greater than 1. So if we look at a few different exponential functions here, so for instance, here we've got this function which is going to be about 1/2 to the x power. The red function here is going to be about 4 to the x power, and this blue function that's falling down, I think I have as negative. Excuse me, I should be looking forward. So it's going to be about 1/3 to the x power. And the reason that I can read these off is I can look at how steep the function climbs or falls. Functions that go up and to the right will always have a base that's bigger than 1. So 4 is bigger than 1, and 1.5 is bigger than 1. Functions that fall are going to have the base be less than 1, but it still has to be positive. And I'll go through in the next video and describe what all of these functions look like, common characteristics, common properties of all of these graphs.